Hello everyone, this is the discussion for the numerical integration and differentiation assignment. The first problem in this one is a function called int_est, where we are writing a function to estimate an integral using this Simpson's rule. And this function has two input arguments. The first one, which is x space, is a single scalar value that represents the distance between the x coordinates, and y, which is an n by 1 vector, with n being a odd number, which is a important point here. So in the lecture videos, it was discussed, Simpson's rule was talked about, and it talked about how to use Simpson's rule to estimate integrals using endpoints as well as midpoints of the intervals that you divide the domain into. In this case, at the beginning we don't know how many intervals we're going to use, but we can figure this out by the number n, how many points it is. So the formula for this is given in the lecture videos, and since we don't need to compute anything related to the function, because we are just given y values at various x data points. And if you notice, in the formulas, you don't actually need to know the x values, you just need to know the difference between them. And the assumption here is that the x values are uniformly evenly spaced, so just knowing the distance between each one is going to be enough. So if n is 3, then we use 2 subdivisions and and that corresponds to 3 function evaluations, like was talked about in the video. Or in other words, 3 y data points. Yeah, and this was talked about in the videos. The formula's there. This function in general is pretty straightforward. So if it becomes too complicated, then you're probably thinking too hard about it. So yeah, and it's pretty simple. So and again, if you forget the formula, then just go back to the lecture slides, because it's given there. The next question, question 2, we are writing a function called astronaut android, and as was discussed in the opening paragraph of the question, we have accelerometer data, which has more applications than we could name. It's basically we are given acceleration and so we're given acceleration at a bunch of time steps. So we're given acceleration at a bunch of time steps, which is read from the accelerometer. And t-stamp, keep in mind here, is a vector. So it's an array. So t-stamp and accel go together in that t keeps track of time and accel keeps track of the acceleration at every single time step. The initial altitude corresponds to the original point. So in this function we have a rocket, and it is going straight up. So there's only there's only, in terms of the physics and the space, there's only one direction, right? It's just, I guess, either z or y or however you define it. It's just straight up. So the acceleration is either straight up or straight down. So the altitude is then, directly corresponding to that. Basic physics gives us the relationship between the acceleration, the velocity, and position, right? Where position in this case is altitude, since we're dealing with the z. Those relationships are velocity is equal to initial velocity, which the homework assignment says in this case you can assume is 0, plus the integral of acceleration times dt. So you integrate the acceleration with respect to t, and that gives you velocity. Now, remember that both velocity and acceleration are both functions of time, meaning that they change at every time, but we are doing discrete time steps, not continuous functions, and that is what the data is given to you in both T-Stamp and Excel. So you get velocity by integrating the acceleration with respect to time, and then once you have velocity, you can solve for the position by integrating velocity with respect to time. So to compute these integrals, you want to use the function cum_traps, which is a cumulative trapezoidal integration. To do this, you just type help cum_traps and pay close attention to the portion where it specifies with 2 input arguments, because that is the type of function call we're going to want to use here. And once again, this function is also not very complicated, so hopefully you won't write too many lines or spend too much time writing this one. The next question, question 3, we are writing a function to estimate the derivative of a function. Now, the inputs here are, so what we're doing in this function is we have a mathematical function y of x, and we are estimating the derivative of y and the second derivative of y with respect to x. Now, what we are given is n values of y. So we don't know, it's not like we're being given a function handle or anything like that. We are given y data points, and those are in the input argument y values. So we have y, which would correspond to f of x, depending on whatever your notation is, and we are also given h, which corresponds to the step size in the x direction. So the delta x between every 2 xy coordinate pairs is h. So to approximate these derivatives, we're going to use the finite difference formulas, and those are given in the assignment PDF. And keep in mind, in the PDF, you're given forward difference equations, backward difference equations, and central difference equations. They talked a little bit in the lecture videos about what that means and how they're derived. So if you have any questions about that, either go watch the lecture videos again or come to lab and ask. But yeah, the equations are just given to you, so you can use those. So the forward, backward, and central difference equations are what you're going to use. And since the central difference equations require knowing the function value 2 steps to the left and to the right, we're going to use the center difference equations on the data points that are in the center. Whereas on the left endpoints, which correspond to the first 2 values in the y values array, we're going to use the forward difference equations. And for the last 2 points, we're going to use the backward difference equations. And then, as I already mentioned, for all the other data points, we're going to use the central difference equations. So this one shouldn't be too hard, just some indexing to take care of the first 2 and last 2, and yeah, and once again, you're computing the first and second derivative here, which, you know, and the equations are given. So yeah, it's pretty simple, this function. Hopefully it won't take you too long. The next question, question 4, this one is a little bit more complicated, but not really by that much. So in this question, we are dealing with a train. So in this one, train power is the first function we're going to write. And in this function, we are given x and y coordinates at discrete time steps. And so x and y coordinates at various time steps all of which are separated in time by t step. So we're just given, we're tracking the motion of a train in an xy plane, aka the ground, and we have at different time steps different locations for the train. So we're allowing the idea that the track has curves in it and whatnot. So the first thing we're going to do here is given these xy coordinates, we want to compute the distance at every time step. So we have xy coordinates at every time step, and we want to compute the distance traveled in each time step. So the formula is given in the homework PDF. It's just the simple distance formula that we all know from simple basic geometry. So we're computing the distance at every time step first, or the distance traveled from one time step to the next first. So note that when you compute the distance traveled in each time step, this will have one fewer elements than x and y, but we are starting with 0, so we want to make sure the first value in this array is 0, so that's just a simple append that you need to do to make sure that those have the same dimensions. And then once you have the once you have the distance traveled in each time step, then you want to compute the cumulative distance traveled at every time step. And this shouldn't be too hard. You just use the function cumSum, which takes the cumulative sum of the total distance that it's traveled at every time step. So now we have, you can think of, now this is like in your physics or calculus relationships where S is your displacement. You have a displacement array where you have an object moving and you are tracking its total displacement at a bunch of discrete time steps. So to do that, or so given that, once we have that, then we can compute the velocity and the acceleration at every time step. So once you have the cumulative distance traveled, you simply differentiate that twice, or you differentiate it once to get the velocity, and you differentiate it again to get the acceleration. And note that we just wrote a function to do that for us. So that step shouldn't be too hard once you've done question 3 as well. So once you have the derivatives, you have the velocity and acceleration, then you can compute the force on the train at each time step. And there's a formula for that that's given in the assignment PDF. And once you have the force, then you can compute the power, which again is just force times velocity. And remember, you're going to probably want to use an element by element multiplication here, since we have force at several time steps as well as velocity at several time steps. So after we have the force and the power, then we want to know if the force, or if the power at every time step is either brake power or engine power. Now we have this train traveling along, and in order to keep since there is friction on the track, if the net power is 0, then we know that that is being provided by the engine. Or if the net power is greater than 0, we know that that power is being provided by the engine. If the power is negative, meaning that the train is slowing down and losing energy, we know that that power is being so the power is negative, and the engine and the train is slowing down, and that is caused by brakes. And again, we're using the assumption here that the brakes and the engine are not on at the same time. So for that, it's just simply the idea that the power at each time step is either brake power or engine power. And how do you know which one is which? Well, if it's greater than or equal to 0, it's engine power. If it's less than 0, it is brake power. Also worth noting is that we define brake power we define, since we are in a coordinate frame where forward is positive, it's the negative power that is being supplied by the brakes, or that is being absorbed by the brakes. But since we're talking specifically about brake power, it's assumed that the force is backwards. So we just want to know the total power. So it doesn't need to be negative when you have that. So it will be negative after you compute it, but that is merely an indication that it is it's merely an indication that it is that it's a brake power. So once we have an array specifically for brake power, we don't need to have the negative in there anymore. And keep in mind that the power. So now this is getting towards our two outputs, which are brake power and engine power, and the output should contain zeros where there is no power, or when there is no power, or thus preserving. So it's keeping the same size as all of our other arrays. We're starting with x and y. So we have a size for x and y. Distance will be the same size. The displacement, or s, will be the same size as that. V and a will be the same size as that. Force and power. So all of these arrays need to be the same size. So just keep that in mind when you are taking your array of calculated power and separating it into brake power and engine power. So almost done with question 4, almost done with the assignment. One last question, or I guess one last part to question 4, which is another function called train energy. So this uses int brake pow and int engine pow from question 4, or from the function train power, and computes energy at each time step. So energy is the integral of power times dt. So we're just integrating power with respect to time. So the first thing we do is, in this case, we're given a t step but not a t array, and we want to make an array of t values. So we want to start at 0, and then we have increments of size t step, and the total length of this array is going to be the same length as the input int power arrays. So you make a t array, and then you use that to do the integral, which we're going to again just use a prepackaged command, but note it is not the cumulative integral. So in this case we want to use the function trapz rather than cum trapz, because it's slightly different the way we're doing it, since we have energy and time at each time steps. We integrate it that way. So this function is not super complicated, so hopefully it won't give you that much trouble. And I think I've reached the end of the discussion because we're out of questions to talk about. So good luck with your assignments, and see you guys in lab.